In this video, we will look at the mathematical assumptions that lead to expressing measurement uncertainty. To do this, we refer to the Guide to the Expression of Uncertainty in Measurement, known as the GAM, which you can download from the website of the BIPM, the Bureau International des Poids et Mesures, the international organization that governs metrology. The text is available free of charge from the BIPM website, and you can access it using the link found in the additional materials of the MOOC. Let's immediately see what requirements uncertainty must meet according to the GAM. First of all, it must be universal, meaning it must be applicable to all kinds of measurements and to all types of input data used in measurements. In other words, it must be applicable both to measuring the length of a table and to measuring cholesterol levels in the blood. It must also be internally consistent, meaning it must be possible to derive it from the components that contribute to it, regardless of how they are grouped or decomposed into subcomponents. It must also be transferable, which implies that the uncertainty evaluated for one result must be capable of being directly used as a component in the evaluation of the uncertainty of another measurement in which the first result is used. The GAM then tells us that in many applications it is not enough simply to state the result of a measurement. It is also necessary to provide an interval about the measurement result that may be expected to encompass a large part of the distribution of values that could reasonably be attributed to the quantity being measured. It also tells us that the ideal method for expressing uncertainty must provide an interval with a given coverage probability, or confidence level, that the value of the measurand falls within that interval. You can see, then, that the need to refer to probability is beginning to emerge. We have clarified what requirements must be met. At this point, we can ask ourselves how we can define and assess uncertainty in order to obtain this coverage interval. The main difficulty is clear. We have to manage this without knowing the true value of the measurand, which, as we have already seen, is unknown and unknowable. And once again, the GAM helps us, although it rests on a quite strong assumption. In fact, it assumes that all error components due to systematic effects have been identified and that the necessary corrections have already been made. What are the systematic effects? They are effects that always repeat in the same way, such as a bent pointer that always produces the same reading error, or a beam balance with one arm longer than the other. The interesting aspect of errors due to systematic effects is that they can be corrected. For example, in the case of a beam balance, using the double weighting method, the unknown mass and the reference mass are swapped and the average of the two weightings is computed. If, as recommended by the GAM, corrections are applied for all systematic effects, what should we expect? The consequence is that only random effects remain. And what are they? They are those effects that act in a purely random manner and generate random variations in the measured value. As a result, a distribution of values that could be attributed to the measurand is obtained. In cases where only random effects are still present, the values attributable to the measurand can be mathematically represented and described as a realization of a random variable. This, in turn, is mathematically represented by a probability density function, which can be a normal function, also known as Gaussian. Is it the only possible function? No, because depending on how the random effects come into play, the distribution of values that could be attributed to the measurand can be represented by different probability density functions, such as the uniform or the triangular ones. We will later see how to determine which one to use. Now that we have a distribution of values that could be attributed to the measurand, represented by a random variable, what information can we obtain? The first is that the best estimate of the measurand is given by the mean value of the variable. Let us remember that for a continuous probability density function p of x, the mean value is given by this formula. The second extremely useful piece of information also comes from probability and tells us that the estimate of the dispersion of the values about the mean is given by the standard deviation of the distribution, which for a continuous probability density function p of x is given by this other formula. The greater the standard deviation, the wider the dispersion of the values that could be attributed to the measurand, as can be seen in this figure, where the red probability density function has a standard deviation twice that of the blue one. The standard deviation of a distribution can therefore be used to quantify the uncertainty of a measurement result. This gives what the gamma defines as the standard uncertainty, that is, the uncertainty of the result of a measurement expressed as a standard deviation. Note that the gamma recommends using the lowercase letter u for the standard uncertainty and advises not to use more than 2 significant digits when expressing it. To summarize, we have seen that if corrections for systematic effects have been properly applied, the measurement result can be mathematically expressed with a random variable, and the measurement uncertainty can be evaluated by assessing the standard deviation of this variable. It still remains to be seen whether we are able to successfully obtain an interval and a coverage probability, but we will cover this point in detail during a future video.